Capacitance is a fundamental concept in electrostatics and refers to the ability of a system to store electric charge. A capacitor is a device designed for this purpose and consists of two conducting plates separated by an insulating medium such as air or vacuum. When a potential difference is applied across the plates, electrons move from one plate to the other, making one plate negatively charged and the other positively charged. Experiments show that the charge Q stored on a conductor is directly proportional to the potential difference V between the conductors. This relationship leads to the definition of capacitance. Capacitance is defined as the ratio of the charge stored on either plate to the potential difference across the plates. Mathematically, capacitance C is equal to Q divided by V. The SI unit of capacitance is the farad, which is a very large unit, so in practice smaller units are commonly used. To understand capacitance mathematically, consider a parallel plate capacitor. It consists of two large parallel metallic plates, each having area A, separated by a small distance d. The distance between the plates is much smaller than their dimensions, so the electric field between them can be considered uniform. Using Gauss's law, the electric field between the plates is equal to the surface charge density divided by the permittivity of free space. Surface charge density is defined as charge per unit area and is equal to Q divided by A. Therefore, the electric field between the plates becomes equal to Q divided by epsilon naught times A. The potential difference between the plates in a uniform electric field is equal to the electric field multiplied by the separation distance d. Substituting the value of the electric field, the potential difference becomes Q times d divided by epsilon naught times A. Using the definition of capacitance, C equals Q divided by V, and substituting the expression for V, the charge Q cancels out. This gives the final expression for the capacitance of a parallel plate capacitor, which is equal to epsilon naught times A divided by D. This result shows that capacitance depends only on the geometry of the capacitor, increasing with plate area and decreasing with plate separation. When a capacitor is charged, energy is stored in it in the form of electric potential energy. Work must be done to move charge against the electric field. The small amount of work done in moving an infinitesimal charge dq through a potential difference V is equal to V multiplied by dq. During charging, the potential difference at any moment is equal to Q divided by C. To find the total work done, this expression is integrated from zero charge to the final charge Q. After integration, the work done, which represents the energy stored in the capacitor, is equal to 1/2 Q squared divided by C. Using the relation Q equals C times V, the energy stored can also be written as 1/2 C times V squared. This shows that the energy stored in a capacitor increases with the square of the applied voltage. Finally, consider the effect of inserting a dielectric material between the plates of a capacitor. A dielectric is an insulating material that becomes polarized when placed in an electric field. This polarization produces an internal electric field that opposes the original field between the plates. As a result, the effective electric field and potential difference are reduced. Since capacitance is defined as charge divided by potential difference, a decrease in potential difference results in an increase in capacitance. The increase in capacitance is measured by a factor called the dielectric constant, represented by kappa. When a dielectric is inserted, the capacitance becomes kappa times the capacitance in vacuum, allowing the capacitor to store more charge at the same applied voltage.